Good afternoon. During the last part of the previous lecture, I introduced the notion of torsion for a space regular curve, and I explained why the denominator has this structure. It remains to explain why in this definition we are dividing by the length of the velocity vector. The reason why we do that is that we want the torsion to be independent of the parametrization, as the lemma 1.49 says. So let's try to understand why this is true. Suppose that gamma tilde equal to gamma composed with phi is an orientation preserving reparametrization that is phi prime is positive. Let's use the following notation for the Frenet frame associated to gamma tilde. So Frenet frame associated with gamma tilde, T tilde and tilde and B tilde. We want to show that T tilde is T composed with phi and tilde is N composed with phi and B tilde is B composed with phi. That is, the Frenet frame is unchanged. Why this is true? So let's start from proving this one. So according to the definition, T tilde is V tilde T divided by the length of V tilde T. We already computed V tilde in the past. And we found that, so let's see page 25, we found that V tilde of T is phi prime T multiplied by V of phi T. So this implies that V tilde T over the length of V tilde T, this is equal to phi prime T V of phi T divided by the length of phi prime T multiplied by V of phi T, but the length of this vector is the absolute value of phi prime multiplied by the length of V phi T. but the hypothesis on phi was that phi prime was positive, so this is equal to phi prime, and these two terms cancel out. So this is nothing but then t composed with phi, t of phi t, and this proves the first formula. What about the second one? Definition of n tilde says that this is equal to a orthogonal of t divided by the length of a orthogonal, a tilde orthogonal t. Also for the acceleration, we know that there exists a formula somewhat similar to this one. Precisely, we proved in the past that a tilde orthogonal of t, this is equal to phi prime t squared times a orthogonal of phi t. So this implies that a tilde orthogonal t divided by its length this is phi prime t squared multiplied by a tilde t phi t divided by the length of phi prime t squared a orthogonal phi t, but the length of this vector is the absolute value of this function multiplied by the length of this vector. Here there is a square, so the numerator and this factor which appear in the numerator cancel out with this factor which appear in the denominator, and what we get is n of phi t. So this is the proof of this formula here. Now, of course, the third identity follows from the fact that b tilde of t is equal to t tilde of t cross product n tilde of t, and now we can use these two identities, and we can write t of phi t cross product n of phi t, but this is nothing but then t times n evaluated at phi t, that is b evaluated at phi t. So this implies that this is true. Okay, now let's erase this part of the blackboard. And let's prove that tau tilde t, the torsion of gamma tilde coincides with tau phi t. Okay, by definition, what is tau tilde t? This is the quotient of minus b tilde prime t n tilde t divided by the length of v tilde t. And now I use the formula I have on the blackboard. What is b tilde prime t? Is the derivative with respect to the time of this vector here given by b composed with phi. So by the chain rule we get that this is equal to minus phi prime t b prime of phi t multiplied by n of phi t divided by the length of phi prime t times v of phi t. But the length of this vector here is the absolute value of phi prime times the length of this vector here. But phi prime is positive, so this factor and this factor coincide and they cancel out. So this means that we get equal to minus b prime of phi t multiplied by n of phi t divided by v of phi t, and this is nothing but then tau evaluated at phi t. Okay, now we have that tau tilde t is tau tau composed with phi. So this says that the torsion does not depend on the parameterization because the torsion is unchanged. Now we have to consider the case when phi prime is a negative, so it is a orientation reversing parametrization. In this case, the Frenet frame associated with gamma theta is given by the following formulas: t tilde equal to minus t composed with phi, n tilde equal n composed with phi, b tilde equal to minus b composed with phi. Now, in order to prove this formula, you have to make the same computation I made before, using the fact that now phi prime is negative, and this implies that the absolute value of phi prime is equal to minus phi prime. So this is why you get the minus sign in the formula for t tilde. The reason why you don't get a minus sign in the formula for n tilde is that in the formula for the acceleration, I tilde t, you have phi prime t squared times a orthogonal of phi of t. So here you have a square of phi prime, and so you don't see the effect of the orientation reversing parametrization on the orthogonal component of the acceleration. Instead, the reason why you have this sign here is that b tilde is a cross product of t tilde and n tilde. Okay, now it remains to prove this formula. Using these identities. So tau tilde of t by definition is a negative inner product of b tilde prime of t multiplied by n tilde t divided by v tilde of t. Okay, once again, what is b tilde prime is the derivative with respect to t of this composite function. So observe that there is a minus sign here. So you get minus of minus phi prime t b prime of phi t multiplied by n of phi t divided by the length of v tilde t, which is given by the absolute value of phi prime t multiplied by v of phi t, and once again the length of this vector is the absolute value of phi prime times the length of this vector here. Now we are in the case when phi prime is negative, so you have this identity here, and this means that this factor and this factor will cancel out, and what you get is exactly minus b prime of phi of t n of phi of t divided by the length of v phi of t, but this is nothing but tau of phi of t. So this proves that the formula tau prime, tau tilde of t equal to tau of phi of t is true also in this case. Okay. The next result I want to present answer to the following question. What is the geometric behavior of a curve having zero torsion. So from the definition, we get that if the torsion is 0, then the numerator is 0, and this means that B prime is constant. Sorry, B prime is 0, and this implies that B is constant. You could make the following question. You could tell me why from the fact that B prime comma n of t equal to 0 you can deduce that B prime is 0. The answer is that last time we proved that B prime is orthogonal to T and B. So B prime has only one non-zero component along n. This means that if the torsion is 0, this component will be 0, and this means that the vector is 0. So from the fact that B prime is 0, we get that B is constant, but you know by the definition of B that B is orthogonal to the subspace spanned by T and N. So B is orthogonal to the osculating plane. Now, saying that B is constant implies that the osculating plane does not change. We can be more precise than that, and we can say that if gamma is as usual a regular space curve, with at different from 0 for all t in I, then with the following statement holds true: the trace of gamma lies in a plane if and only if tau t is 0 for all t in I. Let's prove this. Okay, let's prove this implication here. So let's suppose that the trace of gamma lies on a plane. Suppose that the trace of gamma lies in the plane P of equation ax plus by plus cz equal to d, and if w is a vector whose components are a, b, c, then this equation here can be written as follows. It can be written as the inner product of a point P of coordinate x, y, z and w equal to d, and this means that we can describe P as the set of points in R3 such that this identity holds true. Okay, so if this is true, then we have that gamma t w equal d for any t. So this implies that the derivative with respect to t of this inner product is 0. But this is also equal to gamma prime t multiplied by w. Why? Because this is a constant vector, so the derivative of this inner product is just the inner product of gamma prime and w. So this says that gamma prime of t is orthogonal to w if we take the second derivative. We can get d2 dt square of gamma t multiplied by w. Of course this is 0, and this is the inner product of gamma second T comma W. So this is 0 and this says that gamma second T is orthogonal to W. What about the vectors which compose the frame? Okay, so T by definition is V of T over the length of V of T. But V of T is exactly this vector here, and this vector is orthogonal to W. So also this one will be orthogonal to W. What about N? N of T is the orthogonal part of the acceleration divided by the length of the orthogonal part of the acceleration. But what do we have here? Here we have that gamma second is orthogonal to W. So gamma second orthogonal to W implies that the acceleration A of T is also orthogonal to W because A of T is orthogonal to this one. And this implies that A orthogonal T is orthogonal to W. Why? Because A of T consists of two components, A parallel of T and A orthogonal of T. So we know that this vector here must be orthogonal to W. This vector here is also orthogonal to W. Why? Because A parallel is parallel to V. But V is gamma prime, and gamma prime is orthogonal to W. So this forces also A orthogonal to be orthogonal to W. The conclusion of all of this is that T of T and N of T are orthogonal to W. What about B? By definition, the unit binormal vector is given by T of T cross N of T. Since B of T is defined through a cross product, then this is a vector which is parallel to W and of unit 1. So this means that there are only two possibilities, B of T equal to plus or minus W over its length. The reason why we divide by the length of W is that B of T must have unit length. Okay, so B of t, by definition, is the cross product of two smooth functions, so this must be a smooth function. And this means that if we take the function t goes to the inner product of bt over length of v, this must be a continuous function, but by the definition, by this identity, we have that this function is equal only to plus or minus 1. So this means that this function here, in order to be continuous, must be constant. Because it cannot jump from minus 1 to plus 1 or vice versa. So if this function here is constant, then b of t is equal to this vector, or b of t is equal to minus w over length of w. So in both cases, b of t is a constant vector, implies tau equals 0. Now we have to prove this direction. So suppose that tau of t, this is 0 for all t in I. From the definition of torsion, this implies that b of t is a constant vector For example, we can write b of t equal to w for all t in I. Okay, now let's compute ddt of the inner product of w and gamma t. This is w multiplied by gamma prime, that is v of t. And this is 0 because t equal v over length of v. Let's write also is orthogonal to bt equal w. But if this is 0, then the function w multiplied by gamma t, this is equal to a constant but this is the equation of a plane, implies gamma t lies in the plane of equation W P equal D. And this is the end of the proof. The next topic of today is the set of Frenet equation. These equations will allow us to understand the behavior of a curve with non-zero torsion. So theorem, actually proposition 1.52. So suppose as usual that gamma is a regular space curve then at every time t in I with k t different from 0, we have the following set of equations hold true. T prime equal length of V k n, n prime equal to minus length of V k t plus length of V k b, and b prime equal minus V tau, sorry, this is a tau n. These equations can also be written in the language of matrices, so we can write Tn b prime. This is equal to length of V times the matrix 0 k 0 minus k 0 tau 0 minus tau 0. Okay, let's prove why this is true. The reason why you need this hypothesis here is that if you have k of t 0, then n is not defined. And if n is not defined, b is not defined. So the Frenet frame is not defined. Implies Frenet frame undefined. So you need this hypothesis. Okay, so why these three equations hold? The first one, it is already known. So t prime equal length of v k n. It has been already proved in proposition 1.35. What about the second one? So in order to prove this equation, I will copy it here. N prime equal minus v kt plus length of v tau b. We have to prove that n prime multiplied by t is minus v k. N prime multiplied with n is 0, and n prime multiplied with b is length of v times tau. So essentially, these three formulas say what are the components of n prime in the direction given by the vectors in the Frenet frame. Okay, let's start from this one. This one follows from this one. Why? Because n prime t is minus n t prime. This follows from the fact that ddt of n multiplied by t, this is 0, and the t prime is given by this formula. So this is n multiplied by v k n, and we get immediately length of v k, because n is a vector of length 1. So the inner product of n with itself is 1. So we proved this identity. What about this one? This is immediate. It follows from here. ddt of n with itself, the ddt of the inner product of n with itself, this is 0, but this is also equal to twice n prime times n. So this says that n prime multiplied with n, this is 0. Now what about the last one, this one? This follows from the fact that n prime b is equal to minus b prime n. The reason why this identity is true is that ddt of n times b is 0 because n and b are orthogonal. And now we use the definition of torsion, which is tau equal minus b prime n divided by length of v. So b prime times n is minus tau v. Sorry, there is a, yes, there is a minus sign, but there is a compensation of sign because of the sign here. So you have length of v times tau. So we prove this one. And now it remains to prove that b prime is minus v tau n, but we already know why this is true. We already proved that b prime t is 0. We already proved that b prime comma b t is 0. And we know, but by the definition of torsion, that the component of b prime in the direction of n is minus tau times v. And from here, this formula follows immediately. Okay, now let's study how announced a few minutes ago what is the behavior of a curve with non-zero torsion. So suppose that gamma is a unit speed space curve and fix P0 in I such that the curvature at T0 is non-zero. Okay, as done in the past, let's consider the third order Taylor polynomial of gamma at T0, which is precisely this point here. We get gamma T0 plus H approximately equal to gamma T0 plus h gamma prime t0 plus h square over 2 gamma second t0 plus h cube over 6 gamma third t0. So I want to say again that approximately equal means that gamma t0 plus h is equal to the sum of these four terms plus an error that has been omitted, which satisfies this formula, sorry, this identity. Okay, now let's try to compute the expressions of gamma prime, gamma second, and gamma third in terms of the vectors in the Frenet frame. In order to do that, we use the fact that the curve is a unit speed. So unit speed means that the length of v equal to the length of gamma prime is equal to 1. So we know that gamma prime is equal to t because t is v over length of v, that is gamma prime over length of gamma prime. Gamma second is t prime, but t prime is kn. More precisely, t prime is k length of v n, but this is 1. What about gamma third? Gamma third is kn prime. Why? Because gamma second is kn. So we get k prime n plus n prime k. I want to write in other order, plus k n prime equal to k prime n plus, now we use Frenet equations for this term, and we get k times minus kt plus tau b. Of course, there is no length of v, so length of v does not appear in this formula because the length of v is equal to 1. So, in conclusion, if you replace all this vector, one remark before going on, all these vectors are evaluated at t0 because I dropped, I did not write explicitly the dependence on t0. We need gamma prime t0, gamma second t0, and gamma third t0. So if you replace the formula for gamma prime, gamma second, and gamma third in th equal gamma t0 plus h minus gamma t0. This is what we call displacement vector. You will find that the function x of h, defined to be the inner product of dh with t, this is approximately equal to h minus k squared times h cubed over 6, yh defined to be dh times n. This is approximately equivalent to k times h squared over 2 plus k prime h cubed over 6. And the last function is z of h. This is defined to be as dh comma b approximately equal to k tau over 6 times h cubed. Okay, now suppose that up to our rotation of R3 t equal t0 is the vector 1 0 0, n which is n t0 is 0 1 0, and b equal bt0 is equal to 0 0 1. And suppose also that up to a translation gamma t0 is equal to 0 0 0. And now let's try to make a picture. So this is the point gamma t0. No, sorry, this is not the good picture, so let me sketch another one. So this is gamma t0. This is the unit tangent vector t, This is the unit tangent vector, no, the unit normal vector n, and this is the unit binormal vector b. So in this picture, the function x of h is given by the length of this segment from here to here. Y of h is the length of this segment, and z of h is the length of this segment. Why? Because we define x of h as dh comma t, y of h as dh comma n, and zh as dh comma b. So essentially dh on this blackboard is the vector having its tail at gamma t0 and is a tip at gamma t0 plus h. So if you want to make a picture, this is dh. So the components of dh in the direction given by t and b are x, y, and z, which are given by this picture: x of h, y of h, z of h. Okay, what can we deduce about x of h, y of h, and z of h? So, since k is always positive, then from the formula for z of h, which is this one, we get that if tau is positive, then z of h positive for h positive sufficiently small. Why? Because if h is positive, we have h cubed, and this is a positive function. If tau is negative, then zh is negative for h positive sufficiently small. What does it mean? it means that the picture I sketched here corresponds exactly to this case. Why? Because ZH, which is the length of this segment, is positive, and this means that positive torsion at T0 implies that gamma passes through this plane. But what is this plane? This is a plane spanned by T and N, so it is the osculating plane. At T0, from below. So this sentence means that at the point T0, the curve gamma, the trace of the curve gamma, passes through the osculating plane from below to above. Of course, if the torsion is negative, then ZH is negative. So this means that the corresponding picture is not this one. But what we can see, we can say it is clear. We can say that gamma passes through the osculating plane from above. So in other terms, if you want to make a sketch in this case, you will get that the curve behaves like this. This is gamma T0. Now gamma T0 plus H is here. Gamma T0 plus H, and this is located below the osculating plane, while before gamma T0 was located above the osculating plane. Of course, please remember that above means the region of the space toward the vector B enters. So here B points upward, so this means that the above region of the plane is this one. Okay, let me check how much time I have. Okay, I think that for today that's all, and I will see you next time. Thank you.